This is Deepak Chopra, and I'm here at Sages and Scientists 2016 with two very distinguished astrophysicists, scientists who are describing basically the origins of the universe and how we know it as it is right now. And Joel and Priya, just want to make sure that people watching us are not academicians. Okay, so they want to understand in basic language what we're going to talk about. So why don't I start with Priya, who's professor of astrophysics at Yale.
Yep.
And so what is dark matter?
Ooh, billion-dollar question. We don't actually know exactly what it is. We believe it's a particle that was probably created at some point in the early universe, but it's a very peculiar kind of particle that it interacts almost not at all with anything else in the universe. So the only property that it has that is of relevance to us is that it has mass. So it exerts gravity. So because it doesn't actually interact with photons and any other charged particles, we don't actually see any emanation of any radiation in any wavelength from it. So it doesn't reflect light, it doesn't absorb light, it doesn't interact with light at all. So the only thing it does is actually impact the motions of particles, because that's what matter does.
And it holds the galaxy together, right?
It holds galaxies together. It provides the gravity that's needed to hold the gravity, the stars in a galaxy, stars, gas, and dust in a galaxy. And also, it's also the sort of scaffolding within which actually very early in the universe galaxies formed to start with. So it's sort of in the driving seat of everything in the universe, but it remains mysteriously unseen.
And if it wasn't there, would we exist right now?
No, we wouldn't.
Okay, so guys, if you don't believe in God tomorrow, just bow down and say, Hail Mary to dark matter. Okay, Joel is professor emeritus at UC Irvine, right? No, UC Santa Cruz. I'm so sorry. Yeah, and he actually is responsible for the double dark theory of dark matter. What do you have to say to what do you have to add to what Priya said?
Well, nothing except to reinforce that dark matter is most of the mass in the universe, the vast majority. We don't know what it is. If it has interactions besides gravity, they must be extremely weak, because we've looked very hard and we haven't seen them yet. I was the one who first pointed out that another popular theory called supersymmetry, which has not yet been verified, naturally predicts the existence of particles like the dark matter particles, these weakly interacting massive particles. It may be that these particles do exist and we're on the verge of discovering them. We might actually start making the supersymmetric particles if we have enough energy at the Large Hadron Collider. That would include making the dark matter particle. We might see the dark matter in various ways, direct and indirect. The experiments are getting much better. It's also possible that dark matter is something completely different. Another popular idea, also connected with other ideas in particle physics, is that the dark matter is something called axions.
Yes.
So those would be a completely different kind of dark matter.
Axion.
Well, Wilczek's main contribution was that name. What happened was that there was a laundry detergent which stopped being sold in the United States. I understand it's still being sold.
He could have called it the Wilczek particle, though.
But he thought that that's such a great name, axion, that it deserves to be the name of this hypothetical particle. So Roberto Peccei at UCLA and Helen Quinn at Stanford had pointed out that there's a certain symmetry that should exist to explain an otherwise difficult to understand fact about the way matter works. It's called the Peccei-Quinn symmetry. And Steve Weinberg said, oh, well, that means there has to be a particle. And Wilczek said, and I propose to call it the axion. The point is that we need to have these axions. They seem to be an essential part of the universe. They don't have to be the dark matter. They could be the solution to this strong CP problem, the thing that Peccei and Quinn were trying to solve, without being the dark matter. But they could be the dark matter. If they are, it's yet a completely different story, and there's an experiment that will detect them if they exist in a certain mass range. It's at the University of Washington. So we're working on all of these things. The nightmare is maybe the dark matter is actually completely invisible. It only has gravity and no other interactions. And then no matter how hard we try, we won't be able to see it. So that's
The
the thing we
invisible
worry
is
about.
real.
Right.
So, Priya, what's a black hole? You remember you're speaking to...
Right. So actually, before I get on to
Yeah.
the black hole, which I could go on and on
Yeah.
about, is that, the other thing that people have tried is to modify Newton's laws and to see if we can argue away dark matter by saying what really happens on cosmic scales is that the Newton's laws of gravitation, as we know, where the force falls off as 1 over distance square, is actually modified in some way on cosmic scales. And so that was, modified Newtonian dynamics was the name of that particular theoretical idea. It turns out that, even sophisticated versions of that theory don't work. And in fact, the death knell are these gravitationally lensed arcs. They cannot produce. They might be able to explain galaxies, the dark matter in galaxies, away by modifying the laws of Newton's laws, but they're not able to describe what is seen and incontrovertibly seen by gravitational lensing.
Well, you spoke about that in your talk, and that talk is available online. So
coming back to a black hole.
Yeah, what's a black hole?
So, in Einstein's theory, the conception is that our universe is this sort of fabric of space-time. That's what the universe is. And that the presence of masses causes little potholes in them. Black holes are just very compact, dense objects that have matter, where they're so densely packed that instead of causing a little divot or a pothole, they actually cause a huge pinch in space-time.
Are they zero volume?
No, they're not zero volume. They actually have a volume that we calculate using a very special sort of region of space around them, which is called the event horizon.
Correct.
So this is sort of a physical region wherein any particle, including light, if it passes through that region, it is lost. That information is lost. We cannot recover it by the way that we know how to recover information. So it's sort of the point of no return. The gravity is so intense that once you cross this boundary, you can no longer get released from the gravity of the black hole. So black holes, you can think of them. So in a way, there's something very intriguing about black holes, aside from the fact that they are the sort of singularity. So the other uncomfortable thing about black holes is that they are a point, they enclose this point called a singularity, where all known laws of physics break down. So we don't actually know how to describe the center of a black hole. And so black holes were discovered mathematically. So they were theoretically predicted. And it took a long time for people to actually find real black holes, which is black holes are also the end states of stars. When stars burn up all their fuel and there's a huge explosion, and sometimes you have several outcomes. If you have a very massive star, you would be left with a very compact, dense object, which is a black hole. So sort of reconciling this material reality of a black hole with the mathematical conception of the black hole, that took a long time and many, many discoveries. And in my opinion, I don't know, Joel, if you would agree with me, that the discovery of the gravitational radiation from these colliding black holes in LIGO probably sort of once and for all made black holes real, right?
Before I get to that, because you mentioned LIGO and Interstellar, the movie.
Oh, yes,
okay,
I loved it.
You enjoyed it.
Very
So
much.
do you think that scenario is ever possible in the
No.
distant future?
No. I mean, it's a speculation. I mean, what was beautiful about the movie was that because they had Kip Thorne, who is, a black belt
He was
general
supposed to be
relativist.
here, but now he's so important, he decided
Well,
not
I think
to
he's
come.
going around the world collecting prizes,
Right.
which is great.
Yeah, we had invited him.
Yeah. So, I think because Kip was involved in the making of the movie, I think he has this very nice line where he says, look, my job was to make sure that we can stretch our imagination and go just a little bit beyond where fact would allow us to be currently and possibly forever. So I think, they stretched it. So I wouldn't take any of those scenarios as happening anytime soon. But I think it was so beautifully visualized, right? I mean, talking about the sort of technology that you were playing with this morning, I mean, the technology, the visualization that they did. For me, one of the neatest things was, I don't know if this has actually been registered by the public. So during the rendering of the shape of light rays as they move around a black hole and the kind of shadows they created, In fact, they solved the real equations. So this visualizing company, Double Negative, solved the equations.
Amazing.
And in fact, Kip noticed something that he hadn't noticed in the mathematical solutions before. So they wrote a scientific paper.
Amazing.
How often do you have Hollywood collaborating with, a top-notch academic
That's
scientist?
amazing.
So I think that was a wonderful movie. And I have to confess, I'm an unadulterated Chris Nolan fan. So
Oh, good. So listen, Joel, you can comment on Priya's question, but I also want to ask you another question. Is the standard model in trouble with what Priya said, the observed observations versus the theories, say the cosmological constant?
Let me first comment on this question of what really proves the black holes. The reason that the LIGO discovery of the gravity waves from two merging black holes, each about 30 times the mass of the sun, is so important is that we had never tested Einstein's theory in what we call the strong field limit. We had tested it at speeds 1/10 the speed of light, 100th the speed of light, 1,000th the speed of light. We just tested it at the speed of light.
Wow.
And it worked. And not only that, the preliminary evidence is that the black hole that formed after the merger was rotating. It's the kind of solution that was found by the Australian physicist Roy Kerr. That's still quite preliminary. I've discussed it with the discoverers, and they're hoping that as they get more data from many more of these observations, they've seen more now, we'll really be able to pin that down. That shows that Einstein was really right. Gravity is geometry. And that means that you have to take the whole theory extremely seriously.
Yeah.
Now, as to whether the theory, the standard model of particle physics and general relativity are in trouble, I wouldn't characterize it that way. I think the way Priya said it at the end of her talk is the right way to think of it. The theories are incomplete. What we're looking for is an encompassing theory that will mathematically include, in a way that is coherent, both quantum theory and general relativity. The reason this is so complicated is general relativity is geometry, whereas...
So gravity is maybe not even a force, just a
No,
distortion
you can think of it
in
as a
space-time
force,
geometry.
But it is caused by this distortion in space-time
Yeah, but
geometry.
it's not like the others.
But how
right?
do you think quantum mechanically about the underlying geometry? We've learned how to do quantum mechanics in curved space-time, but the curved space-time itself is a background in that case. To fully understand how the whole thing fits together is somewhat elusive. There is one known theory that combines them, superstring theory, but that theory lives in 10 dimensions, 9 space and 1 time, and we don't know how to pull our 3-dimensional universe out of
It
that.
lives in mathematical imagination.
Exactly. So there have been a number of breakthroughs that have increased our understanding of the nature of that kind of theory, but we're not there yet.
Okay.
So, which is great.
Of course.
Science is going
That's
to
how
continue
science works. Yeah.
indefinitely, and there are great unsolved problems.
Science
I keep reassuring
is
my
about
students.
everything being wrong till it's
Well-
right for a while, right?
No, well, it's ever evolving. It's ever evolving.
So it's
And-
based on falsifiability,
And I think
right? So-
Joel put it very nicely that, it's very rare that a theory would get completely thrown out.
Correct.
It's often refined and it becomes inclusive, extended.
and transcended to a
Yeah,
new,
yeah.
So final question. I noticed on your cosmic density pyramid, you used to have the eye of consciousness. Where is that now?
As you said, consciousness is one of the big unsolved problems in modern science. We don't know exactly how it works. We don't even know exactly where it is. And as to how fundamental it is, I'm not sure that we know that either.
Is it, in a way, I'm asking you this question, are consciousness and cosmos, in a sense, complementarities? You need both?
Well, if we, in our conscious minds, which are, of course, the product not of our own upbringing alone, but of the entire arc of humanity, all of our culture. Without that, all there is light. This picture that the unseen universe is actually behind all of the light that we see, this is a construct of human consciousness. And it's only a current temporary picture, which no doubt will be superseded by better pictures. when we have a better understanding of the nature of dark matter and dark energy, for example. So it works as far as we can tell. We keep looking for ways that it's failing so that we can see how to go beyond it.
But where those images are being experienced is elusive.
Yes.
So would it be fair to say, Priya, that I'm not speaking metaphorically right now, but literally, you and I and everyone watching us are stardust beings with self-awareness?
Right. Yeah, absolutely. No, I think that, on the one hand, the problem of consciousness is obviously the biggest problem. It's very hard. And so I have like two things I want to say. In 1543, when Copernicus changed the pivot from the Earth to the Sun, he could not have imagined that in 2016, yesterday, we sent out a probe to a comet that is going to, in 7 years, bring back a spoonful of material from there. He could have never imagined that, right? So I remain open and optimistic that we might be able to crack this one. However, I also believe, and this comes from humility, that there is no reason that we have the cognitive capacity to figure everything out in the universe. And maybe there are some problems that are not quite tractable given the limitations that we have and the apparatus that we have.
So we're almost at the end of our podcast, and you can come back to it on YouTube, on Chopra.com, on ChopraFoundation.com, on Jayo.com/SAS16, and many other locations. But before I say thank you and goodbye, Priya, you have a book which is available right now, and in bookstores, Amazon, online stores. I wish I had a copy of it right now, but we'll show it to you later. Yeah. Tell us about the book.
Yeah, the book is called Mapping the Heavens, and it really tries to talk about how the radical scientific ideas have revealed our current knowledge of the cosmos. So it's sort of a historical, conceptual study of the history of ideas in cosmology.
And Joel, you have two books that I've read now so many times. So anytime I need to explain anything
with
like...
my wife.
Yes, with Nancy Abrams.
All the best writing and many of the best ideas are Nancy's.
Yeah. So, in that book, you describe chaotic inflation, or what you call eternal inflation, with the Las Vegas metaphor. You do it much better than I can. So would you share that with us in say 2 minutes?
So you can think of little pieces of the universe as being like coins that fall out of slot machines continually. And every moment there's a coin that gets either twice the size or half the size. And if it's twice the size, there are two such coins. So the coins are constantly changing. And on the floor, there's a little screen that has a very small diameter hole. The coins that get smaller and smaller and smaller and smaller, just by chance, they happen to get the tails rather than the heads, they eventually get so small that they fall through the hole. And those develop into individual universes. And our universe could have started that way. So the slot machines and the flipping coins, that's eternal inflation. And the way a coin turns into a universe, that's the Big Bang.
So if your mind is not reeling with bewilderment, then you don't deserve to exist. I just want to close with a favorite poem of mine from Rumi. He says, "Exchange your cleverness for bewilderment." Thank you for joining us. Thank you, Priya.
Thank you very much.
And thank you, Joel.
Thank you.